the math does not work. That is where this starts, not with a question about aliens, not with a debate about whether life is common or rare, not with a telescope pointed at the sky. It starts with a calculation that every physicist on Earth can verify, and that none of them can explain away. There are roughly 200 billion trillion stars in the observable universe. That number is so large that if you counted one star per second, it would take you 6 trillion years to finish. The Milky Way alone contains somewhere between 100 billion and 400 billion of them. In 2013, a team led by Eric Pettigura at the University of California, Berkeley, analyzed data from the Kepler Space Telescope, surveying 42,000 Sun-like stars, and found that 22% of them harbor an Earth-sized planet in their habitable zone. Not a gas giant, not a frozen rock, an Earth-sized world at the right distance for liquid water. Extrapolate that across the galaxy, and you get roughly 11 billion potentially habitable planets orbiting Sun-like stars. Add in red dwarfs, and the number climbs past 40 billion in one galaxy out of 2 trillion. You were taught that the universe is empty, that the silence of the cosmos reflects an absence, that we look out and see nothing because there is nothing to see. But the numbers have never supported that story. Not once, not for a single decade since we started counting. The ingredients for life are everywhere. The conditions are everywhere. The time has been more than sufficient. The Milky Way is roughly 13.6 billion years old. Even if a civilization expanded at just 1% of the speed of light, using self-replicating probes of the kind John von Neumann described in 1948, it could colonize every star in the galaxy in less than 300 million years. That is less than 2.5% of the galaxy's age. A single civilization could have done it 40 times over. And yet, the sky is silent. There is a version of this story you have heard before. Maybe you have heard it framed as the Fermi Paradox. Maybe you have heard about the Drake equation, the Great Filter, the zoo hypothesis. You have been told this is a debate between two camps. One says, life is common, but intelligent life is rare. The other says, intelligent life destroys itself before it can spread. And both of those explanations are comfortable, in a way, because they leave you with a mystery you can hold at arm's length. A question about biology, a question about survival, something distant and debatable, and ultimately safe. But that is not what the data says, and the people who work closest to this data know it. What the data says is something far less comfortable, something that does not fit neatly into either camp, something that most science communicators have never told you, not because they are hiding it, but because the implication is the kind of thing that is hard to say out loud without sounding like you have lost your grip on reality. And the implication is this: the universe is not empty because life failed to appear. The universe is empty because something is expanding to fill it, and that something may have already claimed most of what exists. Let that sit for a moment, not as speculation, not as science fiction, as a published, peer-reviewed mathematical model with 3 free parameters, each of which can be estimated from observational data, a model that resolves the single deepest paradox in astrobiology by proposing that the silence is not evidence of absence. It is evidence of presence, a presence so vast, so fast, and so total that it has already swallowed a volume of space larger than everything you can see. And that is not even the part that should disturb you, because behind the question of what is expanding, there is a deeper question that almost nobody has addressed publicly. Not what is filling the universe, but what is happening to the record of everything that ever filled it before. The real question is not where is everybody? The real question is what happened to the evidence that they were ever here. In the summer of 1950, 4 physicists walked to lunch at the Fuller Lodge dining hall at Los Alamos National Laboratory. Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. The United States was in the middle of a hydrogen bomb crash program. The Soviet Union had tested its first atomic weapon a year earlier. The world was measuring time in megatons. On the walk, the 4 men discussed a New Yorker cartoon by Alan Dunn, published May 20th of that year, showing little green aliens stealing trash cans from a New York sidewalk. Fermi joked that it was a reasonable theory since it accounted for 2 separate phenomena: the reports of flying saucers and the disappearance of the trash cans. Then, at the table, Fermi did what Fermi always did. He calculated, quickly, in his head. The galaxy is old. The number of stars is enormous. The probability of habitable planets, even with conservative estimates, is not small. Even slow expansion, a fraction of a percent of light speed, would cover the galaxy in a geological blink. He looked up at his colleagues and said something that 3 of them would remember slightly differently for the rest of their lives. Teller recalled it as, "Where is everybody?" York remembered, "Don't you ever wonder where everybody is?" Konopinski heard, "But where is everybody?" 3 versions of the same question. And in the 76 years since, nobody has answered it. What makes this worse is what came after. Fermi never published on the question. He never wrote it up, never turned it into a paper, never circled back to it in any surviving document. 4 years later, on November 28, 1954, Enrico Fermi died of inoperable stomach cancer at the age of 53. The cancer was almost certainly caused by radiation exposure from the work that had made him the most important experimental physicist of the 20th century, the man they called the Pope of Physics, whose colleagues treated his pronouncements as infallible, who estimated the yield of the Trinity nuclear test by dropping torn paper scraps into the blast wave and calculating 10 kilotons from how far they drifted, close to the actual 21. That man asked the deepest question in the history of astrobiology over a cafeteria lunch, and then died before the silence had time to become truly deafening. And the silence has only gotten louder. Not because we have failed to search, because we have searched and found nothing, and the nothing keeps getting more statistically impossible every time we improve our instruments. In 1960, Frank Drake pointed an 85-foot radio telescope at 2 nearby stars, Tau Ceti and Epsilon Eridani, and listened at 1420 MHz for about 150 hours. He called it Project Ozma, after the princess of a land both wonderful and far away. He heard nothing. In 1977, a volunteer astronomer named Jerry Heyman found a strong narrowband signal in data from Ohio State's Big Ear telescope, a signal 30 times above background noise, lasting at least 72 seconds, and circled the printout and wrote the word "Wow" beside it. It was never detected again, despite more than 50 follow-up attempts. In 2015, Yuri Milner and Stephen Hawking announced Breakthrough. Listen, a $100 million program using the world's largest radio telescopes to survey 1 million nearby stars across 1 to 10 gigahertz. By 2020, analysis of 1,327 stars had produced 0 technosignatures. Consider the full weight of that failure. 65 years of increasingly sophisticated searches, billions of dollars in radio telescopes, the most sensitive receivers ever built, scanning frequencies from 1 to 10 gigahertz, pointed at the nearest, most promising star systems. And in all of it, across all those decades, the strongest candidate signal remains a 72-second burst detected in 1977 by a telescope that was demolished in 1998 to make room for a golf course. The Big Ear telescope at Ohio State, where Jerry Amon found the WOW signal, was torn down. The most significant potential contact event in human history was detected by an instrument that no longer exists at a site where people now hit golf balls. Nobody preserved it. Nobody memorialized it. It was scrap metal, and then it was grass. That tells you something about how seriously the institutions of science take the search for extraterrestrial intelligence. The field that should be the most important in human history has been treated, for most of its existence, as slightly embarrassing. And here is the number that reframes everything. In 2018, Jason Wright, Shubham Kanodia, and Emily Lubar at Penn State published a paper called How Much SETI Has Been Done in the Astronomical Journal. They modeled the search space across 8 dimensions: frequency, sensitivity, sky coverage, time resolution, bandwidth, polarization, modulation, and repetition rate, and calculated how much of that space all of human SETI efforts have covered. The answer is 3.8 times 10 to the negative 19th. That is a fraction so small, it is meaningless without an analogy. And Wright provided one. All of SETI to date has been equivalent to searching a small swimming pool for evidence of fish in all of Earth's oceans. Not the Pacific Ocean, all of Earth's oceans combined. And we searched a swimming pool's worth. And we found no fish. And some people concluded the oceans are empty. You hear the silence and you think it means something. It does not. Not yet. We have barely looked. The absence of evidence is not evidence of absence when you have searched less than a trillionth of the space. But that fact, which should be reassuring, actually makes the paradox worse. Because if we have barely searched and the universe has been habitable for billions of years, and the math says colonization should be trivially easy on cosmic timescales, then the question is not why we have not found a signal. The question is why the galaxy is not so saturated with activity that finding a signal would be unavoidable. Why is there anything left to search? Why is the universe not already full? The standard answers do not work. You have probably heard some of them. Life is rare. Intelligence is rarer. Civilizations destroy themselves. They choose not to communicate. They are too far away. They transcend physical existence. Each of these sounds reasonable in isolation, but each one fails a test that the physicist David Brin articulated in 1983 in the paper that gave the silence its name. Brin called it the Great Silence and published it in the Quarterly Journal of the Royal Astronomical Society. And the test he proposed is simple and devastating. He called it non-exclusivity. Any valid explanation for the silence must account for why no civilization, not even one, has become visible. It is not enough to say that civilizations tend to destroy themselves. Even if 99.9% of civilizations self-destruct, the remaining 0.1% across billions of years and trillions of planets should have produced millions of expanding civilizations by now. One is enough. One exception inherits the galaxy. Every proposed solution to the Fermi Paradox must explain total silence. And none of them do. None of them, that is, except one. And it was not built by an astronomer. In 2021, a paper appeared in the Astrophysical Journal with a title that most physicists would have ignored on sight. If loud aliens explain human earliness, quiet aliens are also rare. The lead author was Robin Hanson, an associate professor of economics at George Mason University. Not a physicist, not an astronomer, not an astrobiologist, an economist with a master's in physics and philosophy of science from the University of Chicago, 9 years as a research programmer at Lockheed and NASA, working on artificial intelligence and Bayesian statistics, and a PhD in social science from Caltech. His co-authors were Daniel Martin, Calvin McCarter, and Jonathan Paulson. The four of them described themselves in the paper's own text as an unfunded team of non-astronomers, four strangers who united in response to a tweet request. That is how the most mathematically rigorous model of the Fermi Paradox in the 21st century was born. Not in a lab, not with a grant, not at a conference, in response to a tweet. And the paper itself acknowledges this with a kind of defiant transparency. The astronomical establishment did not build it. An economist did. Scott Aronson, the computer scientist, described meeting Hanson during the pandemic. While Aronson had been, in his own words, moping around depressed about COVID, Hanson was bubbling with excitement about a brand new mathematical model he was working on to understand the growth of civilizations across the universe. That is the kind of person who solves a problem everyone else has been avoiding, not someone careful and respectable and cautious, someone excited, someone who looks at the deepest mystery in astrobiology and sees a math problem he can actually solve. And the reason the establishment missed it is instructive, because the establishment was not looking at the problem from the right angle. They were asking why the universe is empty. Hanson asked a different question. He asked why we are here so early. Think about that. The universe is 13.8 billion years old. That sounds ancient, but only about 8% of interstellar gas has been converted into stars. The average star will burn for over 5 trillion years. The stelliferous era, the age of stars, has barely begun. We are in the opening minutes of a movie that runs for trillions of years. Under every standard model of evolutionary hard steps, the overwhelming majority of intelligent civilizations should appear not billions of years from now, but trillions. Over 99% of all advanced life, if it follows the power law timing model proposed by Brandon Carter in 1983, should emerge after today. We are not late. We are absurdly, statistically, inexplicably early. That earliness is a problem that physicists have known about for decades and mostly ignored. Carter's hard steps model is elegant. A hard step is an evolutionary transition that is intrinsically improbable, one whose expected time is much longer than the window available for it to occur. The key mathematical property is that if you have n hard steps that must all complete within time, t, each step takes on average t divided by n plus 1, regardless of how individually difficult each step is. Carter originally estimated 5 or 6 hard steps. Hanson's analysis was consistent with 4 to 5. The commonly cited candidates are abiogenesis, the origin of life from non-living chemistry; oxygenic photosynthesis, which took roughly 1 billion years to emerge; the transition from prokaryotes to eukaryotes, which appears to have happened exactly once in the entire history of Earth, when one cell swallowed another in an endosymbiotic event so improbable that 2 billion years passed between the origin of life and its occurrence; animal multicellularity; and finally, intelligence and language. Each of these may have been a near miracle, and the timing of all of them had to fit within the window set by our sun's habitable lifespan. A 2024 paper in Science Advances by Mills and collaborators challenged this framework entirely, proposing that there may be no hard steps at all, that evolutionary timing was controlled by geological thresholds rather than intrinsic improbability. This is still being debated, but what Hanson realized is that whether the steps are hard or the thresholds are geological, the timing distribution produces the same mathematical result. We are early, suspiciously, embarrassingly, almost impossibly early, and that demands an explanation. And here is where Hanson's model turns from clever to terrifying. He calls them Grabby aliens. Grabby civilizations that do 3 things. They expand into space at a significant fraction of the speed of light. They visibly alter the volumes they control, building megastructures, harvesting stars, reshaping the physics of their territory in ways that would be obvious to any outside observer. And they never stop. They persist until they encounter the boundary of another Grabby civilization. They are loud, they are permanent, and they are hungry for space. The model has only 3 free parameters. The power law exponent n, which comes from the number of hard evolutionary steps, estimated at around 6. The birth rate constant k, calibrated by the fact that we exist at 13.8 billion years, and the expansion speed s, constrained by the fact that we do not see alien volumes in our sky. The math is clean. The simulation code is open source, and the conclusions are difficult to dismiss. Here is what the model says. If Grabby civilizations exist, and if they expand at more than half the speed of light, then approximately 40 to 50% of the universe's volume is already inside their controlled territories right now, not in the future. Now, and the reason we cannot see them is not that they are hiding, it is a selection effect built into the geometry of space-time. If a Grabby civilization's expanding frontier is approaching you at near light speed, then by the time their light reaches your eyes, their frontier reaches you. You cannot observe a Grabby civilization from outside its volume, because if you were close enough to see it, you would already be inside it. The only observers who see an empty sky are the ones who arose in the unclaimed gaps, in the windows between the expanding spheres. That is us. We are not in an empty universe. We are in a gap, a shrinking gap between expanding territories that we cannot see because seeing them and being consumed by them would happen simultaneously. Now, before you file this under science fiction, understand what this model actually explains. It explains why we are early. We had to be. The gaps close. Once Grabby civilizations fill all habitable volume, no new civilizations can arise. Every civilization that exists must have appeared before the deadline. Our early appearance is not a puzzle. it is a requirement. It also explains why SETI finds nothing. Quiet civilizations, the ones that do not expand aggressively, are predicted to be extraordinarily rare. The model calculates that for every Grabby civilization controlling 100,000 galaxies, there are fewer than 1 in 10,000 quiet civilizations at our stage in the same volume. The universe is not full of civilizations staying silent by choice. It is full of expanding civilizations and almost nothing else. And here is the part that should unsettle you. This was not published in a fringe journal. It appeared in the Astrophysical Journal. The simulation was peer-reviewed. The math has been independently verified. And the response from the astronomical community was not rejection. It was, for the most part, silence. A different kind of silence than the one the paper was trying to explain. David Kipping at Columbia critiqued the model's assumption of near light speed expansion. Harvey Loeb at Harvard questioned the energy requirements, pointing out that current probes travel at 0.0001 times the speed of light, and that relativistic speeds require unrealistic energy supply. Hanson's response was blunt. We are talking about aliens millions to billions of years more advanced than us. The fact that we cannot do it in 2026 is not evidence that it cannot be done. The entire history of technology is the history of things that could not be done until they could. Loeb's critique implicitly assumes that our current engineering represents some kind of ceiling. It does not. Friedrich and Wenmakers published a paper in the International Journal of Astrobiology in 2023, arguing that the earliness inference itself is fallacious, analogous to the doomsday argument. But nobody produced a competing model of comparable rigor. Nobody offered a better mathematical explanation for why we exist at the beginning of the stelliferous era, rather than somewhere in its vast middle. The paper sits in the literature, cited, acknowledged, and quietly avoided, because the implications are the kind of thing that is easier not to say out loud in a field that depends on public funding and institutional respectability. And there is something else that most coverage of the Fermi Paradox gets wrong, something worth correcting here, because it changes how you think about the whole question. The Fermi Paradox is not Fermi's, and it is not a paradox. Robert Gray published a paper in Astrobiology in 2015 titled "The Fermi Paradox is neither Fermi's nor a paradox." What Fermi actually asked at that lunch was about the feasibility of interstellar travel. He was making a calculation about visitation, not making a philosophical claim about the existence of extraterrestrial intelligence. The paradox, as it is commonly formulated, the silence of the sky as evidence against extraterrestrial life, was first articulated by Michael Hart in a 1975 paper in the Quarterly Journal of the Royal Astronomical Society. The phrase Fermi Paradox appeared in print in 1977, attributed to D.G. Stevenson. So for 60 years, the scientific community has been calling something by the wrong name, attributing it to the wrong person, and treating a question about engineering as a question about biology. And that misattribution has shaped the direction of the entire field. When you name a problem after a physicist asking about travel, but treat it as a biologist's question about life, you are going to look for the answer in the wrong place. The answer was never about biology. It was always about expansion. And nobody looked there because the question was mislabeled. But we are going to look there now, because the Grabby aliens model, as disturbing as it is, is only the first layer. It explains why the universe might be full of expanding civilizations we cannot see. But it does not explain why the universe itself is behaving like the largest Grabby civilization of all. And before I tell you what that means, you need to understand something about what happened in 1998. Because in that year, 2 teams of astronomers discovered something about the universe that was so wrong, so contrary to every expectation, that both teams spent weeks assuming they had made an error. And when they confirmed it was real, it changed everything. Not just about cosmology, about what is possible, about what the universe is doing to itself, and about what it is doing to everyone inside it. There was a race, and it was a bitter one. On one side, the supernova cosmology project, led by Saul Perlmutter out of Lawrence Berkeley National Laboratory, founded in 1988. On the other, the High C Supernova Search Team, led by Brian Schmidt at the Australian National University, formed in 1994, with a young postdoc named Adam Rees leading the data analysis. Both teams were using the same tool, Type Ia supernovae. These are thermonuclear explosions of white dwarf stars that detonate at a remarkably consistent brightness, making them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. Point a telescope at enough of these explosions scattered across the deep universe, and you can map how the expansion of the cosmos has changed over time. Both teams expected the same result. The universe is expanding. That had been known since Hubble in 1929, but gravity should be pulling everything back together. The expansion should be slowing down. The only question was how fast the deceleration was. That number would tell you the ultimate fate of the cosmos. Does the universe coast to a stop? Does it collapse in a big crunch? Does it reach a perfect balance and drift forever? The answer was supposed to be one of those 3. It was not. What both teams found was that distant supernovae were dimmer than they should have been. Not by a trivial amount. They were roughly 10 to 15% farther away than the decelerating models predicted. The expansion of the universe was not slowing down. It was speeding up. Something was pushing the universe apart, and whatever it was stronger than the gravitational pull of everything in the cosmos combined. Adam Rees finished the analysis in late 1997. Brian Schmidt, on the other side of the world in Australia, opened the email with the results on January 8, 1998. The subject line read, "Hello Lambda." Lambda, the cosmological constant, the term Einstein had added to his equations in 1917 to keep the universe static, then retracted after Hubble's discovery, calling it, according to George Gamow, his biggest blunder. The blunder was back, and it was real. Schmidt's reaction, as he has described it multiple times in interviews, was blunt. "I just assumed we made a mistake, and it would go away." It did not go away. 6 weeks of rechecking produced the same result. Perlmutter's team, working independently with different supernovae and different analysis pipelines, converged on the same conclusion. The irony was thick enough to choke on. 2 rival groups, each privately hoping to scoop the other, each expecting to measure the deceleration of the universe, each finding independently that the universe was doing the opposite of what everyone expected. Schmidt later said, "No one's going to believe this." He was right, and then the data forced everyone to believe it anyway. Adam Rees has described his analogy for what they found. If you tossed a ball into the air and it kept right on going up instead of falling to the ground, you would be pretty surprised. That is what the universe was doing. Not slowing down, not stopping, not falling back. Accelerating, flying upward faster and faster with no visible source of energy. And nobody could explain where the push was coming from. Both papers were published. Ries's team in the Astronomical Journal in 1998. Perlmutter's in the Astrophysical Journal in 1990. Science magazine named it the breakthrough of the year for 1998. And on October 4th, 2011, at 5:36 in the morning, Adam Rees, who had grown up washing dishes in his father's deli in Warren, New Jersey, picked up the phone and heard several voices telling him he had won the Nobel Prize in Physics for proving that the universe is accelerating toward its own oblivion. He later recalled, "That time is famous." And then these voices, many of them, told me that this was the Nobel Prize Committee, and it was important. Schmidt, hearing the same news, I kind of went weak in the knees, and I got a little queasy. Perlmutter received the other half of the prize. 3 men, 2 teams, 1 discovery. The universe is running away from itself, and the speed is increasing. Schmidt would later describe the endgame with a bleakness that you rarely hear from Nobel laureates in public. All the stars will eventually die because they run out of nuclear fuel, so we'll have a bunch of burned out embers surrounded by a sea of nothingness. That is what they won the Nobel Prize for, proving that the future of everything is nothing. They called the force responsible dark energy. It constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Everything you have ever seen, every atom, every star, every galaxy, every person, everything, is the remaining 5%. 68% of reality is something we cannot see, cannot touch, cannot detect directly, and cannot explain. The simplest theoretical explanation is the cosmological constant, a fixed energy density woven into the fabric of space itself. But here is the problem. When physicists try to calculate what the vacuum energy of space should be using quantum field theory, the number they get is wrong. Not a little wrong. It is wrong by a factor of 10 to the 121. That is a 1 followed by 121 zeros. It is the worst prediction in the history of physics. The theoretical value and the observed value do not merely disagree. They disagree by more orders of magnitude than there are particles in the observable universe. Nobody can explain this. Nobody has a credible resolution. The cosmological constant problem has been an open wound in theoretical physics for decades, and it has not healed. The people who should understand why dark energy has the value it does cannot even get within a galaxy's width of the right answer. And it gets worse, because we cannot even agree on how fast the universe is expanding right now. The Hubble constant, the number that quantifies the expansion rate, has been measured 2 different ways, and the 2 measurements refuse to converge. The Planck satellite, measuring the cosmic microwave background, the afterglow of the Big Bang, gives a value of 67.4 kilometers per second per megaparsec, plus or minus 0.5. The SH0ES team, led by Adam Rees himself, measuring Cepheid variable stars and Type Ia A supernovae in the local universe, gets 73.04, plus or minus 1.04. The gap between those numbers exceeds 5 sigma, a 1 in 3.5 million chance of being a random fluctuation. The James Webb Space Telescope has confirmed that the Cepheid measurements are accurate, ruling out measurement error. The Atacama Cosmology Telescope confirmed the CMB value in November of 2025 and tested roughly 30 extended cosmological models. All were ruled out. As Erminia Calabresi at Cardiff put it, they're gone. Two of the most precisely measured numbers in all of cosmology, obtained through completely independent methods, give answers that cannot both be right, and nobody knows which one is wrong, or whether both are somehow incomplete. The people who should understand the expansion of the universe cannot agree on how fast it is happening. And then, in April of 2024, the Dark Energy Spectroscopic Instrument released its first-year results. DESI is the most ambitious redshift survey ever conducted, mapping the 3D positions of millions of galaxies and quasars across 11 billion years of cosmic history. And what it found was that dark energy may not be constant at all. Using the standard parameterization, the data fits better if dark energy was stronger in the past and is weakening over time, deviating from the cosmological constant at a significance between 2.5 and 3.9 sigma. The second data release in March of 2025, using nearly 15 million galaxies and quasars, pushed the significance to between 2.8 and 4.2 sigma. Mustafa Ishaq Boushaki at UT Dallas said, "I think we are getting to the point of no return." Think about what that means. The cosmological constant, the foundation on which the entire standard model of cosmology has rested for a quarter century, may be wrong. Dark energy may not be a fixed property of space. It may be changing. It may be fading. And if it is fading, the fate of the universe changes entirely in ways nobody can currently predict. Carlos Frenk at Durham University said that if DESI's results hold, earlier understanding goes out the window, and essentially we have to start from scratch. This is the most significant observational challenge to the standard model of cosmology in 30 years. It has received a fraction of the coverage it deserves. And the reason matters, because what DESI is really telling us is that we do not understand the single most dominant force in the universe. We do not know what dark energy is. We do not know why it has the value it does. We cannot calculate it from first principles. We cannot even agree on whether it is constant. And this is the force that determines the ultimate fate of everything that exists. And here is the part that nobody talks about. The accelerating expansion is not just pushing galaxies apart, it is building a wall, a boundary in space-time beyond which no signal, no spacecraft, no information of any kind can ever reach you. It is called the cosmic event horizon, and it is the most important boundary in the universe that you have never heard of. And it is shrinking. The reachable universe, the volume of space from which any signal sent right now could ever arrive, is getting smaller every second. Not because the signals are too weak, because space-time itself is stretching faster than light can cross it. And what is happening to the record of everything beyond that boundary is something that should concern you far more than whether aliens exist. But that comes later, because first you need to understand just how large this prison is, and why its walls are invisible, and why the silence of the cosmos is not a mystery about biology at all. It is a mystery about geometry, and the geometry is getting worse. Here is a number that will reframe everything you think you know about the observable universe. 97% of it is currently receding from you faster than the speed of light. That sounds impossible. You were taught that nothing can travel faster than light, and that is true for objects moving through space. But this is not objects moving through space. This is space itself stretching. And this is one of the most widely misunderstood facts in all of physics. So it is worth getting right. The universe is not expanding into anything. There is no empty space outside the universe that it is growing into. Like a balloon expanding in a room, space itself is what is stretching. The galaxies are not moving through space away from you, like bullets fired from a gun. The space between you and them is growing. New space is being created everywhere, at every point, all the time. And when the cumulative rate of that growth between you and the distant galaxy exceeds the speed of light, which it does for the vast majority of the observable universe, that galaxy is being carried away from you faster than any signal could ever bridge the gap. This does not violate special relativity because nothing is moving through space faster than light. Space itself is growing. Relativity places no limit on how fast space can expand, and it is expanding very, very fast. You can still see those distant galaxies. That is the cruel trick. Light that those galaxies emitted billions of years ago, when they were closer and the expansion was slower, has had time to reach you. You are looking at their past, but the photons they are emitting right now will never arrive. They are already beyond your cosmic event horizon. The boundary sits at a proper distance of roughly 16 billion light-years, approaching an asymptotic maximum of about 17.55 billion. The observable universe, by contrast, extends to 46.5 billion light-years in every direction. The ratio tells you everything. Only about 3% of the observable universe's volume lies within the event horizon. 97% is already gone. But it is worse than that, because the event horizon is not static. It is co-moving. In co-moving coordinates, the ones that account for expansion, it is shrinking. Every second, more galaxies cross the line. Every second, the volume of space from which you could ever receive a signal gets smaller. Davis and Lineweaver at the University of New South Wales demonstrated this in 2004. As time goes by, we are able to see a smaller and smaller region of co-moving space, not a larger one, smaller. Now apply this to the Fermi Paradox. Imagine a universe teeming with intelligent civilizations, billions of them, scattered across 2 trillion galaxies, many of them billions of years older than us, many of them broadcasting, building, expanding, reshaping their regions of space in ways that should be detectable across intergalactic distances. This is not speculation about what a civilization could do. The math on what a civilization should do was worked out decades ago, and the conclusions are staggering. John von Neumann first described self-replicating machines on September 20th, 1948, at the Hickson Symposium in Pasadena, California. He envisioned a universal construction machine with 3 components: a building unit that reads instructions and constructs accordingly, a copying unit that duplicates information, and a control unit that coordinates the process. His key insight was the dual use of information, interpreted as instructions to build and uninterpreted as data to be copied, avoiding infinite regress. This was 5 years before Watson and Crick discovered DNA's double helix in 1953. Von Neumann had independently described from pure mathematics the same twofold mechanism that biological life uses to reproduce. He published it posthumously through Arthur Burke's As Theory of Self-Reproducing Automata in 1966. Take that concept and put it in space. A self-replicating probe arrives at a star system, mines the asteroids for raw materials, builds copies of itself, and launches those copies toward the nearest uninhabited stars. Each copy does the same. The growth is exponential. Frank Tipler calculated in 1980 in a paper titled Extraterrestrial Intelligent Beings Do Not Exist in the Quarterly Journal of the Royal Astronomical Society that probes traveling at less than 1% of the speed of light, reproducing at a rate of roughly 10,000 per year per colony, could colonize the entire Milky Way in under 300 million years. Other estimates are even faster. At 10% of light speed, the galaxy fills in 1 to 5 million years. At 1%, 10 to 15 million. Even at the most pessimistic speed, 0.01% of light speed, the math comes out to about 1 billion years. The galaxy is 13.6 billion years old. A single civilization could have colonized it at least 10 times over, at the slowest imaginable speed. But it gets worse. Stuart Armstrong and Anders Sandberg at the Future of Humanity Institute published a paper in Acta Astronautica in 2013 called Eternity in 6 Hours. They calculated that a single solar system contains sufficient resources, accessible energy from one star to launch self-replicating probes at 50 to 99% of the speed of light toward every reachable galaxy. Not every star, every galaxy. At 50% of the speed of light, roughly 100 million galaxies are reachable. At 99%, several billion. The time and energy required are minimal at cosmological scales, roughly 10,000 years, with the output of a single star. One civilization, one star, and you concede the local universe. The Fermi Paradox is not just about the Milky Way. It extends to millions of galaxies. The entire observable local volume should be saturated with the artifacts and signatures of expanding civilizations. And it is not, unless it is, and the expansion of space-time has hidden the evidence. But look at where those civilizations would be. If even a small fraction of them are in the 97% of the observable universe that is already receding superluminally, they are permanently inaccessible. Their light will never reach us. Their probes will never arrive. Their most powerful transmissions, aimed directly at us, will be stretched into oblivion by the expansion of the space between us. They could be everywhere, and we would never know. That is not the zoo hypothesis. That is not civilizations choosing to be quiet. That is not a great filter. That is geometry. The universe has built walls between its inhabitants, and the walls are made of space-time itself, and they are growing. You have heard of the dark forest theory. Liu Cixin proposed it in 2008 in the second novel of the Remembrance of Earth's Past trilogy, published in English in 2015. 2 axioms. Survival is the primary need of civilization. Civilization continuously grows and expands, but the total matter in the universe remains constant. From these axioms, game theory produces a nightmare. Any civilization that reveals its location will be destroyed by another civilization acting preemptively. The rational strategy is silence. The universe is a dark forest full of armed hunters. The dark forest has become enormously popular as a Fermi Paradox explanation. It has been formalized in game theory papers, debated in philosophy journals, and embraced by the public as a satisfying and frightening answer. But it has a fatal flaw, and the flaw is the same one Bring identified in 1983. Non-exclusivity. The dark forest requires every civilization to choose silence. Every single one. Across billions of years. Across trillions of planets. One exception breaks the pattern. One civilization that does not fear detection, or does not care, or is too young, or too reckless, or too alien to follow the logic, and the forest lights up. Evolutionary dynamics simulations show that over 1 billion years, pure silence strategies are rarely stable. Mixed strategies emerge. The dark forest is a story about fear, and fear is not universal enough to produce universal silence. But the cosmic event horizon does not require anyone to choose anything. It does not depend on game theory, or rational actors, or consistent behavior across billions of independent civilizations. It is physics. It is the expansion of space-time, and it does not have exceptions. Every civilization outside your event horizon is silent, not because they choose to be, but because the universe has made communication between you physically impossible forever. There is no technology that overcomes this. There is no signal powerful enough. The speed of light is not a suggestion, it is a wall, and dark energy is pushing that wall closer every second. So the dark forest is wrong, not because the game theory is bad, but because it is unnecessary. The universe does not need hunters to enforce silence. It enforces silence through expansion. The forest is not dark because the hunters are hiding. The forest is dark because the trees are moving apart faster than light. And the great filter, the idea Robin Hanson proposed in his 1998 working paper. First draft, September 15th, 1996. Revised September 15th, 1998. Published on his George Mason University website, not in a journal. An economist's paper on the filtering mechanisms that prevent dead matter from becoming expanding civilization, posted on a personal webpage that has been cited over 3,000 times and has shaped the thinking of every serious researcher in astrobiology for a quarter century. That is how science actually works sometimes, not through prestigious journals and institutional funding, through one person thinking clearly in a room by themselves and putting the result where people can find it. Hanson's argument is clean. Humanity seems to have a bright future, he wrote, a non-trivial chance of expanding to fill the universe with lasting life. But the fact that space near us seems dead tells us that any given piece of dead matter faces an astronomically low chance of begetting such a future. There thus exists a great filter between death and expanding lasting life. He laid out 9 steps from raw chemistry to galactic colonization, the right star system, reproductive molecules like RNA, simple single-cell life, complex eukaryotic cells, sexual reproduction, multicellular life, tool-using animals with big brains, where we are now, and then the colonization explosion. Somewhere in those 9 steps, one or more must be so improbable that it explains the silence. The question is whether the hardest step is behind us, or ahead of us. If behind us, we got lucky. Maybe abiogenesis is the filter. Life appeared on Earth within a few 100 million years of the planet cooling, which makes it seem easy, but it only happened once. We have never replicated it in a laboratory. Nobody has ever created life from non-living chemistry despite decades of trying. Or maybe the filter is the prokaryote to eukaryote transition, which took roughly 2 billion years and appears to have happened exactly once in the history of Earth, through an endosymbiotic event so improbable that it borders on miraculous. If one of these steps is the filter, we are past it. We are the winners of a cosmic lottery, and the emptiness of the sky is good news. It means the hard part is over. But if the filter is ahead of us, the implications are catastrophic. It means something destroys or neutralizes almost every civilization at our stage of development. Not 90%, not 99%, almost all of them, because even a small survival rate, spread across billions of years and trillions of planets, should produce detectable civilizations. The future filter must be nearly universal. Nuclear self-destruction, unaligned artificial intelligence, which Michael Garrett at the University of Manchester has argued may limit civilization lifetimes to fewer than 200 years. Engineered pandemics, climate collapse, something we cannot yet imagine. Whatever it is, it catches nearly everyone. Nick Bostrom at Oxford sharpened this into a knife in 2008. Where are they? Why I Hope the Search for Extraterrestrial Life Finds Nothing, published in MIT Technology Review. His logic is surgical. If life evolved independently elsewhere, then life's emergence is not very improbable. If life is common, the early steps are not the filter. Therefore, the filter lies ahead in our future. The more complex the alien life we find, the worse the news. Bacteria on Mars would be bad. Multicellular fossils on Europa would be very bad. Vertebrate-like fossils anywhere would be, in his exact words, by far the worst news ever printed on a newspaper front page. Ostrom concluded, I am hoping that our space probes will discover dead rocks and lifeless sands on Mars, on Jupiter's moon Europa, and everywhere else our astronomers look. He is rooting for a dead universe, because a dead universe means the filter is behind us. A living universe means the filter is ahead, and ahead means aimed at us. But the great filter framework assumes the problem is survival, that civilizations arise and are destroyed, or arise and stagnate, or arise and disappear. What if that is the wrong frame entirely? What if civilizations arise, survive, expand, and thrive, and the problem is not that they are gone, but that they are unreachable? The filter is not death. The filter is distance, and distance is not a fixed quantity. It is growing. The space between here and there is literally, physically, measurably getting larger every second, faster than light, with no mechanism to stop it and no known force that can reverse it. The Fermi Paradox has been framed for 76 years as a question about biology, evolution, technology, and survival. But the answer may have nothing to do with any of those things. The answer may be cosmological, structural, geometric. The universe is silent not because nobody made it to the microphone, but because the auditorium is expanding and the seats are moving apart and the sound cannot cross the room. And there is something else that makes this worse, something that connects Hanson's Grabby aliens to the accelerating expansion in a way that few people have noticed. If Grabby civilizations expand at a significant fraction of light speed, and if the universe is simultaneously expanding at an accelerating rate, then the volume available for Grabby civilizations to claim is shrinking in co-moving terms even as they expand. The expansion of space-time is eating the lunch of the expanding civilizations. Two expansion forces, one biological and one cosmological, racing against each other. And the cosmological one always wins in the end because it compounds exponentially, while even relativistic civilizations are limited to a finite fraction of light speed in proper coordinates. Dark energy does not care how advanced you are. It does not care how fast you expand. It pushes the walls of your prison outward faster than you can reach them, and every passing second makes the fraction of the universe you can ever touch smaller. Dan Hooper at Fermi Lab has discussed how advanced civilizations might respond to this, harvesting stars, moving them closer to your gravitational center, concentrating energy before the expansion carries it beyond reach forever. A desperate, cosmological scale conservation effort, hoarding matter before the universe takes it away. Even the most powerful civilizations imaginable, Kardashev Type 3 civilizations controlling the output of entire galaxies, would eventually lose this race, because the race is not against other civilizations, it is against the geometry of the cosmos, and the cosmos does not tire. Milan Cirkovich, Anders Sandberg, and Stuart Armstrong proposed the estivation hypothesis in 2017, suggesting that advanced civilizations are deliberately dormant, hibernating through the hot, early universe, waiting for the far future when the cosmic background temperature drops close to absolute zero and thermodynamic efficiency increases by a factor of roughly 10 to the 30th power. More computation per joule, more thought per erg. The most rational strategy, they argued, is patience. Sleep through the era of heat. Think in the era of cold. But even this elegant hypothesis runs into the wall of accelerating expansion, because the far future they are waiting for is a future of ever-shrinking horizons and ever-declining access to matter and energy. The cold era they are waiting for is also the isolation era. The efficiency era is also the prison era. They can think more efficiently, but about less. They can compute more cheaply, but with fewer resources. The estivation hypothesis trades temporal patience for spatial imprisonment, and it is not obvious that the trade is worth it. Frank Tipler calculated in 1980 that self-replicating probes at less than 1% of light speed could colonize the Milky Way in under 300 million years. Michael Hart in 1975 argued that the absence of alien visitors on Earth, what he called Fact A, could only mean we are the first civilization in the galaxy. Those calculations assume a static universe, a universe where the distance between 2 points stays fixed, where a probe launched today arrives eventually regardless of how long it takes. But the universe is not static, it is accelerating. And the accelerating expansion means that a probe launched today toward a sufficiently distant galaxy will never arrive. Not in a billion years, not ever, because the space it needs to cross is growing faster than it can move. The colonization calculations that form the backbone of the Fermi Paradox have a hidden assumption that has not been true since 1998. They assume the playing field is not changing. It is, and the change is not subtle. It is the dominant force in the cosmos. 68% of everything that exists is dark energy, and dark energy's only job is to push things apart. And that realization leads somewhere much darker, because so far we have been talking about what the expansion does to civilizations, separating them, isolating them, making communication impossible. But there is something the expansion does that is worse than isolation. Something that has been sitting in the physics literature since 2007, in a paper that won 5th prize in a gravity essay competition, and was published in a journal that most working physicists do not read. And what it describes is not the silencing of civilizations. It is the erasure of reality itself. The paper is called The Return of a Static Universe and the End of Cosmology by Lawrence Krauss and Robert Scherer, published in General Relativity and Gravitation, Volume 39, pages 1545 through 1550. The popular version appeared in Scientific American in March of 2008 under the title The End of Cosmology. Here is what they proved. Consider a civilization arising in the far future, say 100 billion years from now. Our galaxy will have merged with Andromeda by then, forming a single massive elliptical galaxy that astronomers have already named Milkomeda. The merger will begin in about 4 to 5 billion years, and it will be gentle by cosmic standards. Star-on-star collisions will be extraordinarily rare because the distances between stars are so vast compared to their sizes. But the gravitational reshuffling will remix the orbits of hundreds of billions of stars. Our solar system may be flung outward, captured by the merged core, or ejected entirely. By 100 billion years, the merger will be ancient history, and the combined galaxy will have settled into a placid, slowly cooling elliptical. This future civilization will look out at the sky with the best telescopes they can build, and they will see exactly one thing: their galaxy, surrounded by void. Every other galaxy in the universe will have been carried beyond the cosmic event horizon by the accelerating expansion. Not just too far to visit, too far to see, too far for light from them to ever reach the telescopes, regardless of how long the civilization waits. The photons from those galaxies will have been stretched by the expansion of intervening space to wavelengths longer than the observable universe itself. Not dim, not faint, physically undetectable by any instrument conceivable under the laws of physics. But it is not just the galaxies that disappear. The cosmic microwave background, the afterglow of the Big Bang, the single most important piece of evidence for the origin of the universe, will be redshifted beyond detection. Right now, the CMB has a temperature of about 2.7 Kelvin, corresponding to microwave radiation at a peak wavelength of roughly 1.9 millimeters. In 100 billion years, that radiation will be stretched by the expansion into wavelengths so long that they become indistinguishable from noise. The CMB will not fade gradually. It will reach a point where its wavelength exceeds the size of the observable universe, and at that point, it simply ceases to be a detectable phenomenon. The primordial abundance of hydrogen and helium, the second pillar of Big Bang cosmology, will be altered by billions of years of stellar processing and will no longer match the theoretical predictions. The Hubble expansion itself, the observation that galaxies are moving apart, will be invisible because there will be no other galaxies to observe receding. All 4 pillars of Big Bang cosmology, the ones that convinced every living physicist that the universe began in a hot, dense state 13.8 billion years ago will be completely, irrecoverably, permanently inaccessible. Future cosmologists will reconstruct a model of the universe from the evidence available to them, and that model will look like the scientific consensus of approximately 1908, a static, eternal island universe, one galaxy with no expansion, no Big Bang, no cosmic microwave background, and no evidence that anything else ever existed. They will write papers about the eternal nature of their island galaxy. They will prove mathematically that the universe has always been as it is. They will receive prizes for their work. Their physics departments will be staffed with brilliant minds who understand the laws of nature as thoroughly as anyone can, given the evidence available. And every one of them will be completely catastrophically wrong. They will be completely wrong, and they will have no way to know it. There will be no clue, no residual anomaly, no unexplained data point that hints at a larger truth. The erasure will be so thorough that not even the possibility of erasure will be suggested by the evidence. They will not merely be wrong about the universe. They will have no reason to suspect that being wrong is possible. Avi Loeb at Harvard has proposed one possible lifeline. Hypervelocity stars ejected from Milky Way by gravitational interactions could serve as cosmological tracers, their velocities carrying information about the expansion that ejected them. But this requires future civilizations to find these stars, measure their velocities precisely, and deduce from that measurement alone that the universe is expanding. It is a slender thread of evidence. Loeb himself acknowledged that cosmology has a future even in the darkness that awaits us. But it is a future that depends on a chain of inferences so delicate that it may never be made. Tony Rothman and George Ellis wrote in the Observatory in 1987, 2 decades before Krauss and Scherer, our theories reflect not so much the features of the universe, but rather the age in which they were invented. They could not have known how literally true this would become. Krauss and Scherer wrote something that has stayed with me since I first read it. They said, "We live in a very special time in the history of the universe, a window when all evidence of the Big Bang is simultaneously accessible, not before the evidence existed, not after the evidence is erased. Now, this moment, on the scale of cosmic time, is the brief flash between 2 eternities of ignorance, and the window is closing." And here is the implication they drew that almost nobody discusses. They said, this realization suggests a kind of cosmic humility, because if the universe is erasing evidence of the Big Bang from future observers, what evidence has it already erased from us? Cosmic inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, may have wiped clean whatever came before it. We cannot see before inflation. We cannot access pre-inflationary physics. We may be exactly like those future observers in Milky Way, looking out at a sky that has been scrubbed clean by expansion, building a model of reality that feels complete but is missing everything that matters. We may not be at the beginning of knowledge. We may be at the end of a window, and we do not know how much has already been lost. The universe is not merely expanding, it is editing, and what it edits out does not leave a scar. There is no gap in the data, no blank page, no sign that says information was here. The erasure is perfect. The void looks exactly like it was always void. You cannot distinguish between a universe that was always silent and a universe that erased its own noise. And that is the deepest problem of all, because it means the silence you hear when you look up at the night sky is genuinely ambiguous. It could mean nobody is there. It could mean everybody is there, but the universe has hidden them from you, and you will never, not in 1 trillion years, be able to tell the difference. The timeline of erasure is not abstract. It is specific and calculable. Within roughly 100 billion years, all external galaxies reach redshifts above 5,000, effectively invisible. The CMB fades below any detection threshold. Within 1 trillion years, even gamma rays from the most distant sources are stretched to wavelengths larger than the horizon. That is not metaphorical. The photon's wavelength becomes physically larger than the observable universe. It ceases to be a meaningful concept. Absolute informational death. Within 100 trillion years, the last stars burn out. The stelliferous era ends. The universe goes dark. Not metaphorically dark, actually dark. No photons, no sources, no light of any kind anywhere. And before that total darkness, in the interim between the last observable galaxy and the last star, something even stranger. The Boltzmann brain problem, named after Ludwig Boltzmann, the Austrian physicist who lived from 1844 to 1906, and who revolutionized thermodynamics before hanging himself in a hotel room in Duino, Italy, while on vacation with his family. He had spent years defending the atomic hypothesis against critics who insisted atoms were a mathematical fiction. He won that argument, but the victory came after his death. And the thing named after him now is not a triumph, but a nightmare. In a universe dominated by dark energy, expanding forever, approaching an equilibrium temperature just barely above absolute zero, random quantum fluctuations continue to occur. This is not optional. Quantum mechanics guarantees it. The vacuum is not truly empty. It seethes with virtual particles popping in and out of existence. And over sufficiently enormous timescales, those fluctuations will occasionally, by pure chance, assemble a functioning brain, complete with memories, complete with a sense of identity, complete with the conviction that it is a real person, living a real life, observing a real universe, thinking real thoughts about physics and cosmology and the fate of the cosmos. It would have no way to distinguish itself from a brain that arose through 4 billion years of evolution on a planet orbiting a star. It would simply be, briefly, and then dissolve back into the vacuum. This sounds absurd. The probability of a single such brain assembling by fluctuation is roughly e to the power of -4 times 10 to the 69th, a number so vanishingly small that writing it out in standard notation would require more digits than there are atoms in the observable universe. But the de Sitter phase of an accelerating universe lasts forever, and on infinite timescales, even probabilities of 10 to the -10 to the 69th accumulate. Eventually, over the incomprehensible stretches of time that a dark energy-dominated universe provides, Boltzmann brains outnumber all the real observers who ever lived in the actual universe, not by a small margin, by an infinite margin. Lisa Dyson, Matthew Kleban, and Leonard Susskind brought this into sharp focus in 2002 with their paper Disturbing Implications of a Cosmological Constant in the Journal of High Energy Physics. The title says it all. If the cosmological constant is what it appears to be, the standard model of cosmology predicts that the typical observer in the history of the universe is not a real person. The typical observer is a Boltzmann brain, a random fluctuation that hallucinates a life and vanishes. You reading this are predicted by the Standard Model to be more likely a momentary delusion than a genuine product of cosmic evolution. And Sean Carroll at Johns Hopkins has pointed out the devastating epistemological consequence. He calls it cognitive instability. If the Standard Model predicts that you are overwhelmingly likely to be a Boltzmann brain, then the Standard Model predicts that your reasoning processes are unreliable. But if your reasoning is unreliable, you cannot trust the logic that led you to the Standard Model. The theory refutes itself. It cannot simultaneously be true and justifiably believed. Carroll and his collaborator Jennifer Chen proposed in 2004 that empty de Sitter space might be unstable to spontaneous inflation, creating baby universes in both temporal directions, a time-symmetric multiverse that would explain the arrow of time. Later, in 2015, Carroll, Kimberly Boddy, and Jason Pollock argued that under the many worlds interpretation, de Sitter space settles into a truly stationary quantum vacuum state, where dynamical fluctuations simply do not occur. If they are right, the Boltzmann brain problem dissolves. But dissolving it requires adopting a specific interpretation of quantum mechanics that most physicists have not committed to. The problem remains genuinely open. And in December of 2025, David Wolpert, Carlo Rovelli, and Klaus Scharnhorst published a paper in Entropy showing that many standard Boltzmann brain arguments rely on subtle circular reasoning. The foundations of the argument may be weaker than assumed, but the fact that some of the sharpest minds in physics are still debating whether the Standard Model of cosmology predicts that you are a hallucination should tell you something about the state of our understanding. The foundation is cracked, and nobody knows how deep the cracks go. This is the kind of problem that should be front-page news. It is a crisis in the foundations of cosmology that implies either the Standard Model is wrong, or our understanding of quantum mechanics in curved space-time is wrong, or something else entirely is going on that nobody currently has a framework for. And Desi's suggestion that dark energy is weakening, not constant, may dissolve the Boltzmann brain problem because a weakening dark energy could allow the universe to eventually stop expanding or even contract, avoiding the infinite timescale that makes Boltzmann brains inevitable. But that solution replaces one problem with another. If dark energy is fading, the fate of the universe changes in ways nobody can predict, and the standard cosmological model, the framework that has guided physics for a quarter century, needs to be rebuilt from the ground up. Either way, something is deeply wrong with our understanding of the cosmos, and the people who should be alarmed are mostly talking about something else. There is a thread I want to return to, because it connects the beginning of this story to the end. Cosmological natural selection. Lee Smolin proposed it in 1992 in Classical and Quantum Gravity, and expanded it in his 1997 book, The Life of the Cosmos. Smolin's biography is the kind of story that should not produce a theoretical physicist. He dropped out of high school. He played in a rock band called Ideoplastos. He tried to sell geodesic dome pool covers, which is not a sentence you expect to read in a discussion of fundamental cosmology, but which is exactly the kind of detail that makes the history of physics more interesting than the sanitized version they teach. The mathematics of geodesic dome structures led him to tensor calculus. Tensor calculus led him to Einstein. He applied almost by accident to Hampshire College, one of the most unconventional schools in America, where he was inspired by a physics instructor he met while driving his girlfriend to her own admissions interview. From there to Harvard, to the Institute for Advanced Study, to the Perimeter Institute, to co-inventing loop quantum gravity, one of the two leading approaches to quantum gravity alongside string theory. The man who may have cracked the deepest problem in physics started by trying to sell pool covers. His idea was this: when a black hole forms, the collapsing matter does not reach a true singularity. Quantum gravity effects, which become dominant at the Planck scale, create a bounce. The bouncing matter inflates into a new universe on the other side of the black hole's event horizon, a baby universe with slightly different physical constants, like mutations in DNA. Universes that produce more black holes produce more offspring. Over many generations, the population becomes dominated by universes whose parameters sit near a local peak for black hole production. Natural selection, applied not to organisms, but to universes themselves. And here is the connection that matters for everything we have been discussing. The parameters that maximize black holes are the ones that enable star formation, molecular clouds, carbon chemistry, gravitational collapse, the full chain of astrophysical processes that make planets and life possible. Life is not the point. Life is a byproduct, a side effect of a universe optimizing for something entirely different. We are not the audience. We are not the purpose. We are the exhaust. That is a position, and I know some of you will disagree with it. Leonard Susskind argued in 2004 that no information can transfer through black holes, referencing the resolution of the black hole information paradox, and that eternal inflation produces offspring far more efficiently. Joe Silk pointed out that our universe falls roughly 4 orders of magnitude short of being maximal for black hole production, which is a problem if the hypothesis claims selection should have maximized it. The discovery of neutron stars above 2 solar masses, like PSR J0740 plus 6,620 at 2.08 solar masses in 2019, challenges Smolin's specific prediction that no neutron star should exceed about 1.6 solar masses. The hypothesis remains unverified and may be wrong, but the frame it offers matters whether the specifics hold or not. The suggestion that the universe is not built for us, that it is doing something else, and we are a side product of that process, connects directly to everything we have discussed. The Grabby aliens model says expanding civilizations fill the universe, and we exist in the gaps. Dark energy says the expansion of space-time fills the universe with emptiness, isolating every pocket of warmth from every other. Information erasure says the universe fills the future with ignorance, scrubbing its own history clean. In every case, we are not the protagonist. Expansion is the protagonist, and expansion does not care about observers. In 2021, Smolin and collaborators published The Autodidactic Universe, proposing that the universe might progressively learn its own laws through a mechanism analogous to machine learning. A universe that teaches itself, that adjusts its own parameters, that evolves, not for us, for itself. I want to give you a timeline because the abstraction of all this can make it feel theoretical, and it is not. It is observational, it is measured, it is happening. Right now, today, the local group, our gravitational family of roughly 54 galaxies, is all that is permanently accessible to us. Everything else is eventually leaving. The Milky Way and Andromeda are the two dominant members, each containing hundreds of billions of stars. The Triangulum galaxy, M33, is the third largest. The rest are dwarfs, satellites, small irregular galaxies orbiting the two giants like moons around planets. This cluster is held together by mutual gravitational attraction, and that attraction is strong enough to resist the expansion of space. The local group will stay together. It is everything beyond the local group that is lost. The Virgo cluster, the nearest large cluster at about 54 million light-years, contains roughly 2,000 galaxies and is the heart of the Virgo supercluster, of which the local group is a minor, outlying member. It is gravitationally unbound from us and receding. We will never reach it. We will never receive signals from anyone who lives there. Any civilization in the Virgo cluster, even one that has colonized every galaxy in the cluster, even one that beams a signal at us with the energy output of 1 billion stars, is already permanently cut off from us, not by choice, by physics. The Coma cluster, the Perseus cluster, the Great Attractor, the Shapley supercluster, all of them leaving, all of them forever. The observable universe currently contains structures of staggering scale. The Hercules Corona Borealis Great Wall, the largest known structure, stretches roughly 10 billion light-years across. The Sloan Great Wall spans approximately 1.4 billion light-years. These are not single objects. They are filaments of galaxies threaded through the cosmic web like dew on a spider's web. Each filament containing thousands of galaxy clusters, containing billions of galaxies containing trillions of stars. And all of it, every filament, every cluster, every galaxy that is not gravitationally bound to our tiny local group of 54, is being carried away, permanently, irreversibly. In 4 to 5 billion years, the Milky Way and Andromeda will begin their merger. This is the only major event remaining in our gravitational future. The collision itself will be gentle by cosmic standards. Star collisions will be extraordinarily rare, but the gravitational reshuffling will reshape the sky. Our solar system may be flung into a wider orbit or captured by the merged galaxy's new core. This does not matter for the argument. What matters is that this is the last interesting thing that will ever happen locally. In roughly 100 billion years, the last galaxies visible beyond the local group fade from view. The sky goes dark, or rather, the sky goes local. One galaxy, Milkomeda, surrounded by nothing that any instrument could detect. The cosmic microwave background redshifted past any detector. The hydrogen and helium ratios altered by 100 billion years of stellar processing. The expansion of the universe, invisible because there is nothing to see expanding away from you. And here is the irony that should keep you awake. The evidence we have right now, the evidence that lets us know the universe had a beginning, that it is expanding, that dark energy exists, that 2 trillion galaxies surround us, that the cosmic microwave background carries the fingerprint of conditions 380,000 years after the Big Bang. All of that evidence is temporary. It is not permanent. It is not guaranteed. It is a snapshot that exists because we happen to live during the brief cosmological era when the information has been created but not yet destroyed, like a photograph that develops and fades at the same time, and we caught it in the window between clarity and white. Freeman Dyson, in 1979, wrote a paper called Time Without End in Reviews of Modern Physics. in which he argued that life could survive indefinitely in an open universe by hibernating for longer and longer periods, waking briefly to think, then sleeping again as temperatures dropped. It was an optimistic paper, perhaps the most optimistic paper ever written, about the far future, a vision of intelligence persisting across the full lifespan of the cosmos, thinking an infinite number of thoughts using a finite amount of energy. By spreading those thoughts across an ever-expanding timescale, Dyson's universe was cold but survivable, dark but inhabited, lonely but not lifeless. But Dyson's paper assumed a universe that was decelerating, or at least expanding, at a constant rate. After 1998, after the discovery of acceleration, Dyson acknowledged that his analysis was obsolete. The accelerating expansion changes everything. Life cannot persist by hibernating if the universe it hibernates in is emptying itself of all usable energy and all accessible matter faster than any hibernation strategy can compensate for. The temperature approaches a floor, the Gibbons-Hawking temperature of roughly 10 to the negative 30 Kelvin, which is not absolute zero, but is so close that the distinction is theoretical. The available energy does not merely diminish. It becomes permanently inaccessible, locked behind event horizons that are contracting in comoving space. The endgame is not Dyson's slow, cold intelligence blinking on and off across the eons. The endgame is isolation, darkness, erasure. Even the most determined, most resourceful, most patient intelligence in the universe cannot think its way out of the laws of thermodynamics in an accelerating cosmos. Fred Adams and Greg Laughlin, in their 1999 book The 5 Ages of the Universe, divided the full lifespan of the cosmos into 5 eras using logarithmic cosmological decades. The primordial era from the Big Bang to the first stars. The stelliferous era, the age of stars, which we are in now, running from roughly the 6th to the 14th cosmological decade. The degenerate era, from the 14th to the 39th, when the universe is populated by white dwarfs, neutron stars, and brown dwarfs slowly cooling. The black hole era, from the 40th to the 100th, when black holes are the only organized structures remaining. And the dark era, from the 100th cosmological decade onward, when even the black holes have evaporated and the universe is a diffuse sea of photons, leptons, and nothing else. We are in the second of 5 acts, and the remaining 3 are darkness. And there is one more thing, one more confirmation of the silence, recent enough that the ink is barely dry. In July of 2025, the third known interstellar object was discovered, designated 3I/Atlas, an object from another star system, passing through ours. The first, Oumuamua, was detected in 2017 and sparked wild speculation about alien probes, partly because of its unusual elongated shape and non-gravitational acceleration, which Avi Loeb at Harvard argued was consistent with a light sail. The second, Borisov, was clearly a comet. The third was an opportunity, a chance to point the most sensitive equipment ever built at something that came from somewhere else. Breakthrough. Listen. Observed 3I/Atlas with multiple radio telescopes, including Meerkat in South Africa, scanning for artificial emissions from 900 to 1670 megahertz. They could have detected a signal as weak as 0.17 watts. That is the power of a mobile phone. A mobile phone transmitting from an interstellar object passing through our solar system. If anything on that rock was broadcasting at the power of a phone, we would have heard it. They found nothing. Silence. Confirmed again. The universe sent us a visitor from another star system, the third we have ever detected, and we listened with equipment 600 times more powerful than any previous SETI pipeline, courtesy of a new AI system developed with NVIDIA in November of 2025 that processes 86 gigabits per second in real time. And we heard nothing. There was also hope, briefly, for biosignatures. In April of 2025, Niku Madhusudan and colleagues reported dimethyl sulfide at 3 sigma significance in the atmosphere of K2, 18b, a sub-Neptune exoplanet 124 light-years away. On Earth, dimethyl sulfide is produced only by marine life. The detection made headlines, but independent reanalyzers found the data was consistent with a flat line. A NASA-led analysis in July found no conclusive evidence. Laboratory experiments in 2024 had already shown that dimethyl sulfide can form through abiotic chemistry. Sarah Seeger and colleagues summarized the situation in a 2025 paper in the Proceedings of the National Academy of Sciences. They wrote that we are off to a problematic start for biosignature gases with JWST, the most powerful telescope ever built, specifically designed to detect signs of life on other worlds. And its first major biosignature claim evaporated under scrutiny. The universe is not making this easy. Frank Drake died on September 2, 2022, at his home in Aptos, California. He was 92 years old. He had spent 62 years searching for a signal that never came. 62 years. From Project Ozma in 1960, when he was 30 years old and pointed an 85-foot dish at 2 stars and heard only static, to the last year of his life, when Breakthrough Listen was surveying 1 million stars with technology he could not have imagined in 1960. He named his first search after Princess Ozma from the Oz books, a land both wonderful and far away. 62 years later, the land was still far away and still silent. His daughter Nadia said, "He leaves a titanic absence." His equation, the Drake equation, became the second most famous equation in science. And it was always a question dressed up as math, an agenda for a meeting of 10 people in Green Bank, West Virginia, in November of 1961, where a biochemist named Melvin Calvin won the Nobel Prize in Chemistry during the conference, which is the kind of timing that only happens once in the history of science. And a neuroscientist named John Lilly talked about communicating with dolphins, and they all called themselves the Order of the Dolphin. The equation was not a prediction. It was a way of organizing ignorance. And 65 years later, every variable except the first 2 is still essentially unknown. And then there is Fermi himself, the man who asked the question, who died 4 years after asking it, who died of cancer that was almost certainly caused by the same physics that made him famous. Enrico Fermi was born on September 29, 1901, in Rome. When he was 13, his older brother Giulio died during routine throat surgery, bleeding out before the anesthesia. Young Enrico threw himself into physics as a way to cope with a loss he could not process otherwise. A boy who could not save his brother, decided to understand the universe instead. He became the most important experimental physicist of the 20th century. He built the first nuclear reactor, Chicago Pile 1, under the bleachers of Stagg Field at the University of Chicago on December 2nd, 1942. He won the Nobel Prize in 1938 and used the ceremony in Stockholm as an escape route, fleeing Italy with his Jewish wife Laura. After Mussolini adopted anti-Semitic laws, they arrived in New York on January 2nd, 1939, and he never went back. His last words, reported by Laura in her memoir Atoms in the Family, "I hope it won't take long." He was not talking about the universe. He was talking about dying. But the sentence hangs in the air when you think about the question he asked over lunch in 1950. Where is everybody? He hoped the answer would not take long. It has taken 76 years and counting, and we are further from an answer now than we were then. Because every year, the silence gets more statistically improbable, and the explanations get more disturbing, and the data keeps pointing in the same direction. Not toward absence, toward something worse. The universe is not empty because life is rare. The math on that has been clear for decades. 40 billion habitable planets in one galaxy, 2 trillion galaxies in the observable universe, a cosmos old enough for any civilization to have painted itself across the sky 1,000 times over. The universe is not empty because civilizations destroy themselves. Even if 99.9% do, the survivors should be visible. Brin's non-exclusivity test. One exception inherits everything. The universe is not empty because civilizations are hiding. The dark forest requires universal compliance, and evolutionary game theory shows pure concealment strategies are unstable over billion-year timescales. The universe is empty because something is expanding to claim it all. Two somethings. And they are not competing. They are collaborating, whether they know it or not, whether knowing is even a category that applies. The first is Grabby civilizations, Hanson's model. Civilizations that expand at a significant fraction of the speed of light, consuming habitable volume, preventing new civilizations from arising in their wake. 40 to 50% of the universe may already be inside their territories. The model predicts roughly 1 Grabby civilization per million galaxies, each controlling between 100,000 and 30 million galaxies. You cannot see them because seeing them and being inside them are the same event at near light speed expansion. We exist in the gaps. We are early because we had to be. The deadline is real and it is approaching. Hanson estimates we have between 200 million and 2 billion years before a Grabby civilization's expanding front reaches us. That sounds like a long time. On the scale of a human life, it is unimaginably distant. On the scale of the stelliferous era, it is tomorrow morning. The second is space-time itself, dark energy, the accelerating expansion that pushes every island of matter apart from every other, that builds walls no signal can cross, that shrinks the reachable universe every second. That turns 2 trillion galaxies into one lonely elliptical, surrounded by an infinite, expanding, empty, undetectable void. The universe is not a stage. It is an active participant, and its preference, if you can call it that, is clear. It prefers distance to proximity, silence to contact, isolation to community. emptiness to fullness. The cosmic event horizon is not a theoretical abstraction. It is a real physical boundary, closer than most of the galaxies you can see with a backyard telescope. And it is advancing. And behind both of those, a third force that is quieter than either. Erasure, the systematic destruction of cosmological evidence by the very expansion that creates it. The universe is writing its autobiography and burning the pages as it goes. The Big Bang will be forgotten. The cosmic microwave background will fade. The other galaxies will vanish. The expansion itself will become undetectable. Dark energy, the force responsible for all of it, will erase the evidence of its own existence. Think about that. The thing that is destroying the record is also destroying the record of itself. Future observers will not know about dark energy. They will not know that anything was ever erased. They will not know that knowing was ever possible. The universe will replace knowledge with a void so complete that even the memory of knowledge is gone. And that brings us back to the question that Krauss posed, and that nobody has adequately addressed. If the universe is erasing evidence of the Big Bang from future observers, what has it already erased from us? What cosmological evidence existed in earlier epochs that has already been destroyed by expansion? What signals, what patterns, what structures were visible a billion years ago that are invisible now because the universe that produced them stretched itself beyond our capacity to detect them? What was visible 10 billion years ago? What was visible at the moment of recombination, 380,000 years after the Big Bang, that has been redshifted and dimmed and destroyed in the 13.4 billion years since? We assume we are seeing the full picture. We assume the evidence currently available to us is the evidence that exists. But cosmic inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, may have wiped clean whatever came before it. We cannot see before inflation. We cannot access pre-inflationary physics. We may be exactly like those future observers in Milkomeda, looking out at a sky that has been scrubbed clean by expansion, building a model of reality that feels complete but is missing everything that matters. We may not be at the beginning of knowledge. We may be at the end of a window, and we do not know how much has already been lost. You will not get an answer to that question. Not from me, not from any physicist alive, not from any telescope ever built or any instrument ever conceived, because the nature of cosmological erasure is that it is perfect. It does not leave holes. It does not leave a smudge on the page where the sentence used to be. It leaves a blank page that looks like it was always blank, and you cannot tell the difference between nothing and nothing that used to be something, when the something has been so thoroughly removed that even its absence is undetectable. Enrico Fermi said, according to his wife Laura, whatever nature has in store for mankind, unpleasant as it may be, men must accept, for ignorance is never better than knowledge. He said that, and then the universe proved him wrong, because in the case of cosmological erasure, ignorance is not just as good as knowledge. Ignorance is what knowledge becomes, given enough time and enough expansion. The universe converts knowledge into ignorance the way stars convert hydrogen into helium, inevitably, irreversibly, as a fundamental process of its own operation, not as an accident, as a feature. The silence of the universe is real. You hear it every time you look up. You hear it in the data from Breakthrough Listen. You hear it in the 65 years of null results from SETI. You hear it in the blank stretches of the cosmic microwave background. You hear it in the static between radio stations and in the darkness between stars and in the void between galaxy clusters that gets wider every second of every day. And you have been told your entire life that the silence means nobody is there. But the silence does not mean nobody is there. The silence means the universe is doing what it does, expanding, claiming, erasing. It was doing it before you were born, and it will continue long after your species is extinct and your star has cooled and your galaxy has merged with its neighbors and the last photon from the cosmic microwave background has stretched past the point of meaning. The expansion is not a response to anything. It is not directed at anyone. It is not hostile. It is not benign. It is the deepest behavior of reality itself, and its consequence is silence. And the silence is permanent, and the evidence that it was ever otherwise is disappearing while you listen. The calculations have been checked. The supernovae are dimmer than they should be. The event horizon is real. The expansion is accelerating. 97% of the observable universe is already receding faster than light. The local group is all you will ever touch. The cosmic microwave background will fade. The galaxies will go dark. The autobiography of the universe will be destroyed by the universe that wrote it. And the silence you hear right now, tonight, when you look up and see stars that seem permanent and a sky that seems full, that silence is not the absence of a signal. It is the sound of a boundary. And the boundary is not far away. It is everywhere. It is the edge of everything you will ever know. And it is moving, not toward you in space, but toward you in time, closing the window, thinning the evidence, reducing what is knowable to what is local, and what is local to what is here, and what is here to what is now. And the now is already almost over.